So at this stage, the main purpose of doing grinding is basically to produce a fine product. And this fine product should be essentially liberated. So when I say liberated, at the stage of grinding, the main reason or the main purpose should be producing particles, individual particles that are mainly composed of one single phase. So if it was a copper ore, let's say, and let's say the main mineral for the copper was chalcopyrite. So if I decide to do my final stage of grinding, at that stage, what I'm looking for is to produce as much free chalcopyrite particles as possible. And of course, with that, I'm going to have 98 whatever percent gangue. So that gangue essentially needs to be detached from the chalcopyrite, because what I want to do next is once the chalcopyrite is detached from the gangue, I'm going to be using different mineral processing techniques. Typically, in this case, we use frost flotation to separate out the chalcopyrite from the gangue minerals. So that's why this stage of comminution, the final stage of comminution, is very critical. Unless you produce liberated particles, whatever happens next in beneficiation is not going to be a success. So for you to be able to obtain a high grade or a high recovery, the target material or the target mineral needs to be detached from the gangue mineral. And the way we do this is by applying those breakage mechanisms we discussed last time. So although cleavage is not really a breakage mechanism in grinding, we actually use attrition, impact, or abrasion as a way of breaking particles. Why? Because at this stage, what we want is really trying to reduce small particles even smaller. And in this case, we're talking about 100 micron particles or a product of 80 micron particle and so on. So cleavage is not going to do that purpose. So that's only attained if you use mechanisms like attrition and abrasion, because at this stage particles are really fine, really small. They don't have any mass essentially, and therefore you need to rub them against one another, against the grinding media and so on, to be able to obtain finer product size. And in this case, to help the grinding, of course, we use, if it's a ball mill, we use balls. If it's a rod mill, we use rod. If it's a sag mill, which I'm going to talk about later on, we can use bigger rocks or harder rocks to help with the grinding. And we also use some steel media in the case of the sag mills as well. So again, eventually you're going from somewhere around 50 millimeter feet to producing somewhere around 100 micron, 150 micron typically. If you want to go smaller than 75 micron product size in grinding, ball mills are probably going to be very challenging to use. For those, we use different mechanisms, and that step is called ultra fine grinding. I'll talk about that one a bit later on as well. So essentially, something comes from your primary grinding mill or your last stage of crushing, fed into your grinding mill, and then that will be used to crush particle into smaller sizes. And typically you can consider grinding as the final stage of size reduction. So by now you're probably familiar with different types of mills. So you can have either tumbling mills or stirred mills. And tumbling mills include sag mill, autogenous mill, ball mill, and rod mill. And most common stirred mills that we use in the industry these days are tower mill and horizontal mill, which I'm going to talk about individually as well. So what is the action? So as I said, in ball mill, for example, or in rod mill, the mill is essentially horizontal, and we're going to rotate it around an axis, around the given axis. Gizacho, Michael on Silahona, mute Laragana. Okay, that's better. So if the mill is horizontal, in the case of a ball mill, so essentially you have it in a horizontal axis, and there is a tumbling motion applied to it. So it's basically the mill is rotated. And depending on how fast or how slow you rotate the mill, you can actually result in different breakage mechanisms. If you rotate the mill very slowly, so in this case, you're talking about maybe 6, 7 revolutions per minute. That's typically a very slow revolution. Then basically your mill is going to undergo what we call an attrition breakage mechanism. So in this case, essentially, everything will be lifted up and then go back down, lifted up and go back down. So we have that mechanism. I think it's shown in that diagram on the right as A. So all the content in the mill, this includes the particles, the ball, and everything will be lifted up. And before it is actually cascaded, so what should happen is everything goes up and then go back, go up and go back. So there's no lifting of anything happening inside the mill. And essentially in this case, what you get is rubbing particles with one another, rubbing particles with a ball. And therefore, that's why we say in this case, you can, for example, result in loss of wearing of the inside of your ball mill, and you can probably result in a finer breakage. What happens if I turn the mill a bit faster? In this case, we create a motion called cataracting. So basically, you lift everything. Instead of going back down, now the particles and the ball will have enough momentum to be lifted up and go and follow that path shown on the right side as B. So particles and ball are being lifted up, and then they travel in a parabolic motion, and they fall on the toe there, as shown in that arrow there. Okay, so this arrow here, I don't know if you can see it. So instead of going up and down, which is what happens in cascading, particles will be lifted up and follow this trajectory. I hope you can see that laser pointer there. And that's what we call cataracting. And this now includes the balls inside the mill and also the particles inside the mill. So everything cataracts and falls here. So you can actually think of a different mechanism here. So the breakage mechanism now shifts from attrition, which is just rubbing everything with one another, to that of impact, because now the ball and the media and the particles fall back down here at a higher rate, at a higher motion, and therefore everything will be impacted up. And whatever is in here will be crushed at significant impact with the ball, and therefore the mechanism goes from attrition to impact. Okay. So what happens if I continue rotating it at a higher and higher and higher speed? As I mentioned last week, we attain what we call centrifugal force. Everything sticks to the wall, and essentially everything in the mill will be doing this one. So instead of having any grinding happening, you have nothing happening, as everything will stick to the wall. And that is dependent on the so-called critical speed of rotation of the mill. So this picture here shows you if I had to rotate the mill at higher speed, from the green dots there to the blue ones to the purple ones, it is showing increasing rotation of the mill. With increasing rotation of the mill, you tend to increase the critical speed. And once the critical speed is achieved, beyond that, particles will stick to the wall and we essentially get no grinding happening. So that's why it is important to work when you operate a ball mill, for example, or a rod mill. It needs to be a certain percentage of the critical speed. Okay. If it is at the critical speed, that's where you hit centrifugal force, and that's where everything sticks to the wall. So typically we operate them at, say, 50% of the critical speed or 80% of the critical speed. Why do we vary the rotation? The rotation can be varied depending on what breakage mechanism I want to create. So if I want to do finer grinding, what I need to do is reduce the rotation of the mill. Okay. At reduced mill rotation, as I said earlier, you have attrition dominating, and therefore finer particles will be produced. If I rotate the mill at a very high speed, impact will predominate. In this case, coarser grinding is more suited. Okay, that's why we need to operate at different speeds to be able to obtain different grinding or breakage mechanisms, which then will have consequences on the type of particle you produce or the size of particle you produce. And of course, as I said, for example, higher mill rotation, less wearing of the inside of the mill, lower mill rotation, more wearing of the inside of the mill. And therefore, for those, we use what we call liner. So the mill is actually lined. The interior of it will be lined with either steel or a rubber. And depending on, again, what you want to do, the particle size you have in there, how hard they are, and so on, whether you have water or whether it's operated in dry and so on, you can actually have different shapes and different designs. Each of them have their own advantages and disadvantages, especially, for example, if you're using rubber versus a steel liner. Steel liners are usually more durable, they're easier to install, and of course, they have reduced noise associated with them as well. And therefore, they can have some advantages. But most mills that you find will have some kind of liner. For example, this here shows you the interior of a ball mill, which is lined by a steel. Okay, I don't know if you can see the grooves in that inside of the mill, but you can see some lines there, which are basically made there as a liner, and they trap some of the ball that we have inside the mill. So some of the ball will go there, okay, and it actually helps as a protective media itself. If you have sufficient number of balls within those grooves, what happens is every time you rotate the mill, particles will go and fall on those balls rather than the liner itself. And the balls themselves go and hit those balls that are stuck inside the liner. And therefore, now those actually serve as the liners themselves as well. So this is one of the mechanisms people use to actually prolong the life of a liner, and therefore those can be operated for a longer time. So what do you use for grinding? So last week I talked about crushing specifically, and I said you could have one stage of crushing, two stage of crushing, or even three stage of crushing. And I introduced briefly what kind of equipment we use for those crushing stages. And specifically, whether you have one stage of crushing or two stage of crushing depends on the nature of the ore, the downstream processing, and a number of factors. Okay. And the same is true for grinding. So if you do one stage of grinding, especially if you have a softer rock, to do just one stage of grinding is possible. And I know a number of mines which actually have just one stage of grinding using a ball mill. But sometimes you have a competent rock and a hard rock, and therefore you might need to do two stage of grinding. And if you do two stage of grinding, typically you could use a rod mill for the first stage of grinding, which is what we call primary grinding. And then once you do primary grinding with a ball or rod mill, you can then follow that up with a ball mill. And the ball mill will give you the secondary grinding that's required to produce final product. So if that's the case, then material comes from the crusher, goes straight to your primary grinding mill, for example, a rod mill. And the purpose of the rod mill is to produce a coarse particle, say somewhere around 300 micron, which can then be fed into a ball mill. Okay. So basically you have this bridging between crushing and grinding. So I have a crusher, I have a ball mill. Between those two, I have the rod mill, which basically produces finer product for me to be able to do the subsequent grinding. Okay, and you can have different types of rod mills. Some of them have discharge
ዶክተር እናንተ ጋር ድምፁ ሚት ሆኗል። ድምፁ ሚት ሆኗል እናንተ ጋር።
Okay, sorry. I don't know. Randomly mute የሚያደርገው ነገር አለ አንዳንዴ። I think አሁን okay ነው አይደል?
አሁን ይሰማል ይሰማል።
Sorry, I don't know የቱ ጋር እንደተቋረጠ. Anyway, I was just saying that based on the nature of discharge for road mills, we can have either overflow discharge and peripheral discharge, or in this case, a central discharge. And it all depends on how fast particles or how long particles stay inside the mill. So the residence time. Overflow discharge, usually particles spend more time in the mill, and central peripheral discharge, usually particles spend less time inside the mill, and therefore, based on those, we can have either final grinding or coarser grinding. So if I have been to many mining sites locally here and even in other places like Canada and so on, haven't seen a fully operational large scale road mill currently operating. So it's becoming more and more older technology. We definitely use it in the lab, but it's a very small scale. But in a larger industrial scale, in many places that I've gone to, I haven't seen a road mill operating. So that has been now replaced by a SAG mill, semi-autogenous mills, and these are by far the more common. So in many places, either you see SAG mills or even high pressure grinding rods, and I'll talk about those two a bit later on. But in the older days, road mills were typically used as a primary grinding. So the inside of it, for example, for a typical road mill, obviously you have rods inside the mill. Okay, that's what we call a media or grinding media. And these rods could, for example, contain up to 45% volume of the road mill itself. Okay? So they occupy a large fraction of the mill, and usually they are slightly longer compared to the diameter. So the ratio is somewhere around 1.5, even 2.5, so double the width is the length. Okay, and they're purposely assembled in that way. Hence, if you make them, for example, very wide or have larger diameter, bolts may turn inside the mill. If they turn inside the mill, if you're not getting them nicely parallel to each other, if the rod turns inside, what happens then is it actually considerably blocks the grinding option. So in this case, grinding happens between the rod and the rod. So one rod hits the other rod, and between that, the particles will be smashed. That's how you actually result in grinding. So if the rod is free to turn inside, what happens is basically you lose that parallel contact between the rod and the rod, and you basically result in no grinding. To prevent that, you have to have that length to diameter ratio of the rod mill spot on, and obviously that will prevent the rods from turning inside the mill. And I talked about critical mill rotation earlier. So in this case, typically rod mills are rotated somewhere around 50 to 70% or 75% of the critical speed. Again, this is dependent on the nature of the product that we seek, and that will be determined based on operation from place to place. So one of the more interesting thing about road mills is actually the preferential grinding happening. So if you look at it, at the feed end, because particles are obviously bigger, and when particles go through or between two rods, you have this kind of shape, a wedge shape, they call it. And at the discharge end, particles are obviously getting smaller and smaller. So what happens eventually is particles are either here at the feed end or somewhere here, and you don't tend to produce very fine particles. You always tend to produce very controlled, narrow particle size distribution in the road mill. And that's one of the main advantages of the road mill. So it's more suited for coarse grinding, no question about it, but it is also good at selective grinding, because if you have fine particles, those fine particles are not going to be impacted upon around here. they're always impacted on somewhere around here, where the wedge shape actually allows them to be impacted somewhere here, and therefore you avoid over grinding, and that over grinding then would mean that you have a very well controlled size associated. So once I do the primary grinding with the rod mill, if I was to use one, the next step would typically be the final stage of grinding. In this case, using the ball. Okay? And therefore, we say ball mill can be considered as your last chance to produce liberated particles. And usually, you have a large media. Again, in this case, we use small steel balls, and the balls can be made from other things. They can be made from ceramic, from steel, and so on. And you have particles and balls inside the mill, and basically the mill is rotated, and you have contact between the ball and the particle, causing the break. And obviously, it's not just ball-to-particle contact. You have ball-to-ball contact, you have particle-to-particle contact, you have particle-to-ball contact. And therefore, in this case, there's a lot of friction, a lot of interaction going on. And because there's this indiscriminate interaction between particles and the media, when I say media, it's in this case a ball, you tend to produce a very wide particle size. So you produce fine particles, intermediate particles, coarse particles, and that's one of the issues related to volume. Okay. And you tend to also produce lots of fine product. Over grinding can be an issue, especially if you're not keeping an eye on the residence sign inside. The media itself, the balls, typically are somewhere between 5 to 10 centimeters in diameter. Most of the places I went to, the part of the ball is actually about 60 millimeters, or 6 centimeters in diameter. That's a typical size most people use. And if you have to do a smaller secondary grinding, then the balls in that case will be slightly smaller. And again, this is to do with as the balls are smaller, increase the surface area, the contact between the ball and particles increases, so that's most suited for finding. Again, I talked about cataracting and cascading, and again, that can be controlled by controlling the volume. But typically, you operate at about 80% of the critical speed when it comes to. So there are a variety of them. So the 100-inch ball mill here, that's shown here, is actually a special type where you can actually feed different ball diameters inside the mill. And because they made it slightly at an angle, you have the feed size occupied by larger balls and the discharge end occupied by finer balls. And you can actually do more selective grinding or preferential grinding, just like the rod mill. But it's not very common. Okay, but you can, if you're very critical about selective grinding happening or preferential grinding happening, you can use a special type of volume. But in many places, it's really not common to see this kind of volumes. But I just showed you here just to tell you that it is a possibility to do preferential grinding. And again, I probably mentioned sometimes balls or sometimes media, just means the same thing. Okay? For a ball mill, the balls are considered media. So ball mill media are simply steel balls, about 60 centimeters, 60 millimeter in size, in diameter, and those are typically the ones used. And in terms of feed rate, you typically feed this maybe about 1 kilo and 2 kilos for every ton of grinding liquid. Okay? And because there's a lot of impact inside the mill, there's a lot of wear on the balls, they tend to reduce in size continuously, so you need to top it up. And for those, you can always load some balls continuously. And I guess that depends on the use of the ball and so on. And here you see a series of ball mills, about 10 of them from an old mine in PNG, Papua New Guinea. It's a copper mine that was operated many decades ago. And again, I just wanted to show you that they can be very useful in large scale operations. And instead, I think it was a copper mine where they used gold about 10 volts of about 5.5 millimeters per millimeter. And just like the rod mill, we can have different discharge. You can have overflow discharge, basically feed comes in, tumbling action inside the mill, and then the product comes out as an overflow. Or there's another one where you have small holes at the discharge end, and if you have that, it's called a grate discharge or a ball mill. And basically, once you do grinding, particles smaller enough can pass through the grate and go to the product, and particles that are coarse will still be impacted. Again, based on the discharge, you can think of different product or natural products. For example, in overflow discharge, particles pass only once they are presented to the discharge end. And in this case, that's just the inside of it, and that's the discharge end of the ball mill. Okay. And in this case, it's more suited for final grinding or regrinding operations. If you have the grate discharge, instead of a hole as a discharge, as an overflow discharge, you have small openings at the discharge. That's what we call grate. Okay. And in this case, particles, as soon as they go to the grate, they will exit. Okay. So you probably reduce the overgrinding slightly. Okay. And therefore it's more suited for coarse particle grinding, and that can be an advantage for it. One of the issues associated with a grate discharge is that sometimes the balls may actually go through those holes and they block. Okay. For example, here you can have the openings of the discharge here blocked by ball, and if that happens, then you'll have issues with capacity. Basically, one, the mill is not operated at sufficient capacity. And the other problem, of course, is you increase overgrinding because you're not allowing fine particles to pass through. And that can be an issue for grate discharge. For a tube mill, I can have different compartments inside the mill doing different things. Okay. So this compartment, you can have, say, a larger ball media, okay, for coarser grinding, then go to the next step. I can even do something else here. You can use either rods, you can use different things to be able to do different type of grinding. So instead of having two ball mills, one after the other, you could actually do everything in one long mill, and that's called a tube mill. And basically, we produce different compartments with different grinding parameters. So as you can see in this picture here, I have coarser media here, slightly larger balls. I have smaller balls here, although they can be coarse grinding here, followed by fine grinding, or other things like rods, or even using hydro. Okay, so if you're using a media of some kind, like a rod or a ball, obviously those are either rod mill or a ball. But there are cases where I don't actually have to add a ball or a rod into the mill. If that's the case, I'm going to be relying on the ratio of hard and soft rods inside the mill. So in this case, say naturally, if the ore has large hard rods and soft material, I can use the hard material to break the soft material. If that's the case, the hard material is basically used as a medium. I don't have to add a rod, or I don't have to add bolts in the mill. And that's, if that's the case, then we have what we call autogenous milling. Okay. So obviously, advantages, if you're lucky enough to have hard and soft bolts, the main advantage for this one would be that I don't need to buy steel media, in this case steel rods or steel bolts, and therefore that is going to save me a lot of money operationally. But on the other side, you also need to make sure that you have sufficient enough hard component in the ore, because if you don't have sufficiently hard proportion of hard rock in the mill, then you have the issue where you actually don't cause any breakage inside the mill. If everything is soft, or if everything is hard, then your grinding efficiency is going to be severely impacted. So what you need to do here is, if there's a situation of hard and soft complement, yes, can happen. But in reality, again, very few operations use completely autogenous means. I know maybe a couple of operations. There was one for a nickel ore, which is a softer ore, and that will use autogenous mills, works fine. But for many operations where you have hard competent rock all over the ore, it's very challenging to just rely on soft hard composition to cause grinding. So in those cases, maybe you can consider semi-autogenous mills. So in this case, instead of completely relying on hard rock, what we want is some proportion of it can be maybe a larger steel medium. So in this case, we use about 125 to 150 millimeter ball sizes. And these are really larger balls, and they can actually assist the breaking. So in comparison, for example, in a ball mill, you would be looking at 60 millimeter or 50 millimeter ball size. But for a SAG mill, you're looking at double the size. So basically larger medium. Okay. The other difference is, in a ball mill, you will be looking at 45% of the mill volume occupied by the ball or the media, but in a SAG mill, only about 10%. So what is going on here is, instead of adding lots of smaller balls in a SAG mill, you have a few larger balls. Okay, and therefore, if you do that, you have the situation called semi-autogenous mills, but that's not the only difference, obviously. So that's one of the main differences between the ball mill and the SAG mill. But a SAG mill is actually very large in construction. Okay, so in this case, for example, typically you could be looking at 4-meter diameter, 5-meter diameter for a ball mill. For a SAG mill, you're looking somewhere around 12 meters in diameter. So very large diameter, which means that you have now particles and ball coming from a very high height from inside the mill, because instead of 4-meter diameter, I have 12-meter diameter, and the impact inside the mill is significantly high for a SAG mill. Okay. Why? Because the ball and the media is falling from a very high distance into the top, into the impact zone. And that's why you probably can reduce, for example, particles which are, say, 200 millimeter in size can be reduced to about 5 millimeter in size in just one go. And that's mainly because in a SAG mill, you have very high impact. And also we rotate them at slightly higher speed rotation as well, somewhere around 85% of the critical speed. Okay. And again, this increases momentum, this increases impact, and therefore impact inside the SAG mill is considerably high. So the picture you see at the bottom there is the one I've taken from one of the gold mines around here. So basically the circle is the 125 millimeter SAG mill media that we use. But the ones on the right are actually the wearing associated with it. So you can also discharge whatever comes from the SAG mill, remove the smaller media continuously. Okay, and I'm just showing you their comparison to show you the impact inside the mill. So that actually can cause a very high percentage wearing inside the mill. Balls will be reduced in size significantly, and that is because of the hard impact inside the SAG. Okay, I don't know if you see that picture clearly, but it's just a rough comparison between a ball mill and a SAG mill. So this is the SAG mill, and this is the ball mill, and this picture is taken from a local mine site here. I think it's only about 5 minutes drive from where we live. It's a very large gold mine, called KCGM, and as you can see there, the picture shows that's what, roughly the scale of a SAG mill for a ball mill is. And obviously, the SAG mill is larger. And one other thing I forgot to mention is also the diameter of a side mill is a lot more shorter compared to its, sorry, the diameter is a lot more larger compared to its length. Okay? So they are shorter in length, but wider in diameter. So just to give you an idea, we're looking at 12 meters wide versus about 4.6 meters long. Okay, that's all to do with creating a large impact inside the mill. And one of the things we use to measure impact of the mill, for example, if you were to operate a SAG mill on daily basis on a mineral processing site, they actually keep an eye on the draw power or the power draw, how much power is being drawn, okay, for the mill, and therefore that gives you an idea of what the impact is or what your grinding efficiency is. Okay, so that's why they keep an eye on the daily operation for some. Okay, another important phenomena when operating a SAG mill is in a SAG mill, because you have hard competent rock and very large steel media, sometimes you have a situation where some of the rocks are actually hard enough and they don't actually grind to a sufficient extent. And we call those scuds. So scuds are somewhere around 50 millimeters in size. Okay, and what happens is once we have produced a scud, which is a hard competent rock, they will just keep sitting inside the SAG mill. We keep rotating the SAG mill, they don't break, so they keep circulating. So you have to find a way of removing the scuds from the SAG mill. Okay, so to do that, what people do is put a screen next to the SAG mill discharge, and therefore continuously remove the product from inside the SAG mill, screen it out. The fine product can go to, say, a ball mill for secondary grinding. The scuds that you see here are recycled back and crushed again. And this is, I think, another picture from a gold mine down here. And as you can see clearly there, so these are the oversizes that are taken on top of the screen. So what you need to do is you need to take this product here, okay, it's oversized, and send it for a crushing operation. So that's why people probably have a SAG mill and a ball mill, but with that, they have a small crusher next to it. So in this case, you have a SAG mill, discharge comes, okay, so the oversizes, the scuds that are folded on here, they come here and they're crushed. I don't know if you can see, but there's a small cone crusher sitting there, and the cone crusher crushes it, and then it is recycled back to the SAG mill for grinding again. And then the final product from the SAG mill goes to the ball mill, and the ball mill ground further, and then goes to other processing. In this case, would be rotation and so on. So to give you an idea, these are what scuds look like. Okay, so basically here, I just took a sample from this one here, and basically they look like that. But once the cone crusher crushes them, we produce smaller sizes like this one. So it's just giving you an idea of the scale there that we're finding. If you keep this one in the SAG mill, as I said, they just keep rotating, nothing happens, no grinding, your SAG mill capacity reduces significantly. So the smart thing to do would be discharge this as often as possible, crush them with a cone crusher, and now you have produced this. This can be fed back to the SAG mill, and then the operation continues. And in terms of volume, how much we're talking about for the scuds, it could be up to 25% of what's fed into the SAG mill. It can be recycled back for crushing again. So it's, as you can appreciate, it's actually, you know, a significant operation, but it makes sense given the fact that if you don't do this particular operation, then there will be a significant limitation on the use of food. And just for information, if you have something like that, we call this an ABC circuit. Okay? So autonomous linear volume crusher. Okay? And that's typical setup, especially if you have a hard competent. Okay, ultra-fine grinding. So before I talk about ultra-fine grinding, maybe I'm talking a bit faster today. So if you guys have any questions, I think it's better to pause a little bit and give you the opportunity to ask questions. Any questions? Okay, so ultra-fine grinding is not really part of combination if you ask many people. Okay, so maybe for many people, grinding should stop around the boiling stage. Okay, but these days we're not finding high-grade ore. Typically, whatever we discover, although the grade is reasonable, we're actually discovering increasingly complex ore.
ትንሽ ድምፁ ክሊል አይሰማም።
ወየ
ድምፁ ይቆራረጣል።
Okay, your connection ችግር ሊኖረው ይመስለኛል። ምንም አይሰማችሁም?
አሁን ይሰማል።
ኦኬ፣ ምናልባት የኮኔክሽን ችግር ካልሆነ በስተቀር እዚህ ጋር አይ ቲንክ ኦኬ ነው በእኔ ሳይድ። ሆፕፉሊ ሪኮርዲንግ ላይ ትንሽ ይሰማል ብዬ ተስፋ አደርጋለሁ። አይ ቲንክ ያ የኮኔክሽን ችግር ነው። ኦኬ So as I was saying, these days we're discovering more complex ore bodies requiring finer grinding. Okay, so if then you just want to continue using ball mill as your final grinding stage, the problem is that ball mills are not very effective at a fine grind size. Okay? So they do really well if the final product is somewhere around 100 micron, 150 micron, then ball mills are efficient. If you are wanting to grind something below 80 microns, then ball mills are not that effective. So you need to be thinking about maybe using a different technology. And as a result of that, people came up with different grinding techniques to help with the final grinding. Okay? And one of the reasons for the fact that ball mills are not effective is as you go, say, to about 50 micron, your breakage cannot be by impact, and your breakage may not even be by abrasion, because particles at that final size actually have very small mass, insufficient mass, and therefore you can't rub them against one another, or you can't rub a particle against a medium. So that's when I say rub, in this case, I'm talking about mainly, say, abrasion or impact. Even if I want to crush a particle with a ball falling on it, because the particle is very tiny compared to a very large ball, the conversion in energy is going to be very small. So that's why ball mills below 80 microns usually are not advisable. You will end up wasting a lot of energy. And therefore, that's why people want to come up with a newer technology, and fusion mills or stud mills are actually a substitute for that. So there have been a lot of different technologies here, power mills, verti mills, and so on have been designed and have been used maybe in the last 30, 40 years. They have been an incoming technology. So what's the main difference? The main difference from, say, a tumbling mill, like a ball mill, the mill itself is erected vertically, and you put a screw agitator inside the mill, and that screw agitator is what mixes the particles with the media. On top of that, the media itself, in this case, the ball, is made very, very small. So compared to, say, about 15, 16 millimeters for a ball mill, we're talking about 10 millimeters for stud mill or an fusion. So you have a screw agitator in this picture right here, which rotates, mixes particles with the media. On top of that, you have very tiny balls inside the mill. And basically, this actually helps the grinding energy to be transferred efficiently to the particle. And you end up producing fine particles because we're also using very fine media, very fine balls. With fine balls, as we know, you have larger surface area, therefore contact between the particles and these small balls is very high, and therefore you have an efficient grinding. So in this case, have a feed coming from the top, possibly with water, and you have a screw agitator mixing everything up. Particles will be impacted upon predominantly by attrition, and fine particles will make their way up to the discharge because they're continuously feeding. Large particles fill up the bottom, and therefore they constantly push fine particles up. So you have this situation where fine particles and the small media, small balls, will make their way up the discharge. You have a discharge box here where you recycle the ball. Okay, basically you have a screen separating the ball from the particles, and the grinding media is fed back. The particles will be discharged, and you have the product. And this is by far the most effective technique when it comes to fine grinding. So in this case, you could have, for example, a tower mill or a vertimill, very similar technologies, essentially. And this picture here shows those technologies being applied in different places. Where do you use them? You can, for example, use them in regrinding applications. You can use them for fine grinding and so on. And this table just shows you the application in Australia, but it's actually being adopted in many places around the world. And what I want you to focus on is the product size. So as you can see here, most of the product size that we desire from this mill is less than 80 micron. As I say, ball mills are not effective for particle product size of 80 micron or less, and therefore vertimills or stud mills predominate those purposes, so those kind of grinding. Again, you can say, okay, it's not necessarily a combination operation. Maybe you may not have it in your combination circuit, but they're becoming a lot more predominant these days when it comes to grinding or when it comes to ultra fine grinding. So I don't know how much you know about regrinding, but maybe I should mention a little bit about regrinding. So when I say regrinding here, usually what happens is, let's say you do your final grinding step with a ball mill, okay? Produce particles somewhere around 100 micron, let's say. That goes, say, to a flotation operation. In flotation, we separate the target from the gangue minerals, but sometimes you have the target mineral in the gap. Okay? So that's basically going to be sent to the tails, was going to be lost. And usually that loss of the target is because it is still locked within the gun. So what you need to do is, although you have recovered some of the valuable, instead of just pumping everything to the tail, you can actually use a regrinding mill, take the waste there, regrind it again, and liberate some of the target particles, and then put them back into, say, your flotation itself. By doing that, now you have liberated more particles. Hopefully, you will have a chance to recover some of the valuable in the flotation again. Okay? And therefore, that regrinding is more to do with liberating more particles so that they can recover. Okay? So in this case, I can do for gold, where gold was recovered first, but then in the tails, you still have some gold. What you need to do is, instead of disposing that, regrind it, liberate more of the particles, put it back in the beneficiation circuit, and then you would try to recover some of the gold that was benefited. So that's the whole point of regrinding. And as you can see here, because you're targeting finer particle sizes, this kind of technology is applied very extensively for regrinding. Okay, so really, how much difference are we talking about between ball mill and SAG mill, or sorry, ball mill and tower mill, or ball mill and stud mills? it can be significant. For example, here is a comparison between a ball mill and a power mill, where they use same machines, very comparable mill power, okay, and they fed that with very comparable particle size. So this is the feed size, okay, plus 8 microns, and then the mill, and this is the product size using a ball mill about 20, and using a power mill about 5 microns. So you go from here to here using very similar mill power for a ball mill, and again from 30 to about 5 micron for a power mill. So as you can see here, the power mill is more suited for finer grinding. What's more, your grinding efficiency is actually very high. So for a power mill, we're looking at somewhere around 87%. For a ball mill, we're looking at somewhere around 48%. Okay? And also power consumption a lot less for the power mill. Okay? So very significant advantage. So why? Again, as I said earlier, in power mill or in vertimills, we use very small media, and that small media has a very high surface area. That improves contact between the media and the particles, and it helps with grinding efficiency very significantly. Whereas in a ball mill, my ball is 50 millimeters, 60 millimeters in size. My particles are, say, 50 microns. That's a very big mismatch, and that's why, because I have smaller surface area for contact between particles and ball, my grinding efficiency is significantly reduced when it comes to ball. Okay, so that's why we need to pick the right technology when using different grinding operations. Okay, for power consumption, again, it's another comparison between a ball mill and power mill. Okay, so in this case, there's just a comparison between product size. Okay, so in this case, if your idea is to produce about 80 micron, ball mill and the power mill consume pretty much around the same power. If my target was to produce somewhere around 20 micron, the power mill uses about 40 kilowatt hour per ton. So these ones are for the power mill, while the ball mill takes about 160 kilowatt hour. Again, as you can see, significantly high, about 4 times. So that's why we say again, the power mill or the vertimills are a lot more efficient in terms of achieving same reduction, okay, as compared to the other. Okay, I will probably mention a little bit about, I don't know if this is widely available elsewhere, but this is one of the recent technologies that came out from Australia. It's called IsaMill. So instead of having the stirred mill or the aspiration mill vertically, this is actually a horizontal stirred mill. So the difference between the one I showed you earlier and this one is inside the cylinder, you have discs instead of a screw agitator. Okay, so what's the difference here? So in vertimills, you have screws going inside the mill and agitating everything. Here in the IsaMill, you have discs constantly rotating. So it comes from one end and goes inside the crushing chamber or the grinding chamber, where the feed material is the particles, and you have very fine media, which are shown here in ceramic media. So the particles, the media, will be impacted upon significantly by these rotating discs, and therefore attrition becomes very, very high. And again, in this case, because we're using very tiny bolts, high surface area, good contact between particles and the media, very efficient grinding. And this is actually invented out of necessity. In Australia, we have Mount Isa. It's an area in Australia where they have a very significant base metal deposits. The problem with those base metal deposits is it's a very fine grain. So they would need to grind to about 10 micron, 12 micron to liberate the particles. And this is actually a very challenging operation. To grind particles to about 10, 12 micron takes a lot of energy. Okay, and therefore, if they use a normal ball mill, they're not going to get that time. And therefore, they have to come up with a technology that helps them grind to that fine size, and IsaMill is basically invented as a result of that. And this is just an example of IsaMills, where they use it, for example, for zinc ore to produce about 15 micron product, or lead ore about 12 micron product. Another example for McArthur River, again, a very challenging base metal deposit, lead zinc ore deposit, where they have to nail everything to about 7 micron, very nightmare situation. And at McArthur River, they have a number of these IsaMills and operational in grinding. And this is another example in Canada for lead zinc concentrate grinding, and I mentioned about KCGM earlier. So for KCGM, they actually use it for pre-treatment. So in this case, maybe it's going to be too complicated to talk about this for you guys, but essentially what they have is they have a gold ore, they separate the gold using flotation. So the gold is mainly in pyrite, they floating this they float it first, produce a concentrate, and that concentrate is sent to leaching after being floated. And typically, if you just send everything to leaching, those particles are larger, doesn't actually leach very well, and it gives you very poor recovery of gold. So what they do is they regrind the concentrate, produce about 12 micron particles, which then can be sent for leaching. And at that fine size, particles can be leached. So instead of just feeding the leaching tank with very coarse concentrate, you could actually do grinding, produce a finer product, and then that can be fed into your leaching circuit. So in the past, they used to do other things for pre-treatment like roasting and so on. They don't do those anymore. So they replace those with this kind of technology, where again, the idea is producing about 12 micron particles. So that's why I said earlier, ultra fine grinding depends on your operation. Maybe you can use it for comminution if you are here in McArthur River or in Mount Isa. You probably would have to use it in comminution circuit. But in KCGM, we use it for pre-treatment purposes to prepare the concentrate for leaching. So again, it's not one operation for every place, but they can be used for different purposes. Okay, so probably want to mention this again. So what's happening recently? What are some of the common trends in comminution circuit? So the idea has always been reducing the stages of crushing and the stages of grinding as much as possible. So if you don't have to grind something to 100 micron, you don't have to. If you can get away with 500 micron, that's the best. Because the less grinding you do, the more energy you save. That's just the way it is. Okay, so people have been trying to do as little stage of grinding as possible, as little stage of crushing as possible. And that can be done, for example, by using an equipment that can take coarse particles. And that's by using an equipment that can give you a higher reduction ratio, and so on. And recently, people have come up with technologies like autogenous crushing and high pressure grinding rolls. Last week, I told you we're going to talk about high pressure grinding rolls, so I'll talk about those ones a little bit. But again, with autogenous crushing, instead of having a typical jaw crusher or gyratory crusher, people use a slightly modified crusher, vertically erected. When particles are fed, they are circulated at a very high speed, and it actually does both the crushing and the grinding at the same time. and helps with reducing some of those crushing and grinding mistakes. With high pressure grinding rolls, the difference between these ones and the typical or the conventional roll crushers is the diameter of the roll. Okay? So the diameter of the roll in these ones, in the high pressure grinding rolls, is very large. Okay? So if you compare, for example, to a typical roll crusher that I discussed about last week, in this case, the length to the diameter ratio is about 0.2. Okay? Which means they are wide in diameter, but very short. So why do we make them really large in diameter? We can actually increase the impact of the compression. Okay, so again, if you were following me earlier, I mentioned SAG mills versus ball mills. With SAG mill, we make the diameter really large, and therefore by doing that, we increase the impact inside the mill. Okay, that's basically what we do. And we're doing something similar with the roll crusher as well. So by making the diameter of the roll really large compared to the conventional roll crusher, we actually increase the compression force, okay? And therefore particles are not going to be impacted upon at a very high force, highly compressed, and you can actually produce a finer material compared to the typical roll crusher. And in this case, in high pressure grinding rolls, we produce what we call fragmented particles with residual cracks inside them. Okay, and the fact that you're using large diameter rolls also means that you can take a larger size feed, let's say up to 250 millimeters in size, and they can be operated at higher capacity and so on. But one of the main advantages of roll crusher is here. We produce very high proportion of micro crack inside the particle. What does that mean? It means once you do high pressure grinding roll operation, the next step typically is ball milling, and ball milling becomes a lot more easy. Why? Because you produce lots of cracks inside the rock. Okay, as soon as now you feed this to the ball mill, the grinding operation becomes very, very easy. So that's why people have been using something like these ones for the operation, especially when you have very hard competent rock. It actually works out to be a very good option. To give you a comparison, so this is just a comparison between high pressure grinding rolls and the normal roll crusher. If this was the feed size, okay, this solid line here, for any given size, okay, so somewhere around here, for example, okay, so for any given size from here, feed size, this is the reduction you get for a conventional one. But the reduction you get is very significant for the roll crusher, high pressure grinding. Okay? So reduced, okay, is using the typical roll crusher, but reduced significantly when it comes to high pressure grinding rolls. And this x-axis here is the size, product size. And as you can see, especially for smaller particle size grinding, high pressure grinding rolls will be a lot more effective. Okay, so that's just a rough comparison in terms of what you can expect. Okay, maybe just to mention very briefly, when we operate ball mills are operated usually in conjunction with some kind of classifier or some kind of screen. So you feed the mill, you put a screen next to it. So this is the discharge end. And usually with the screen, you have undersize or fine product, okay, which is Q. And the coarser product is the one that's being recycled back into the mill and crushed or milled. So if I was operating my mill, ball mill at say 100 tons an hour, 100 tons an hour always comes in constantly for the day, for the month, for the year. Okay, 100 tons coming in, 100 tons coming out. Okay, so that's a steady state, a continuous operating. So if I have a screen next to it, then I have what I call recycling or recirculating rate. So something has to come back, which can be given by say the T, and this is essentially your cost fraction. Okay, so the cost fraction can be said is measured by a T, the new feed is a Q, and the product is a Q, constantly inflating at 100 tons. The circulating load is given by whatever you recycled back, a T, plus the new feed, Q, which is now going into the mill, divided by whatever goes to the mill, or divided by whatever is discharged from you, which is a Q. Okay? And in this case, if I was to operate my mill at 100 tons per hour, what is recycled back could be 250 tons per hour. So that's actually quite significant. Okay? So that's why we say here, the usual range for recirculating load can be somewhere between 100 and 350%. Okay? When I say 350%, so in this case I have 100 ton going in continuously to the mill, and then I have 350 ton recirculating back. Okay? So at any given time, you could have 350 ton, 450 ton in the mill. Okay? And that's why it is significant. And therefore, you need to keep an eye on circulating the load. And again, this is something to do with controlling the grind size, controlling the product that comes. I'm doing this because I want to remove the discharge or the product as quick as possible, screen it out, and then it's better to crush oversized, okay, rather than keeping everything in the mill for long. Because if I do that, I'm going to increase over grinding, and my operation is not going to be. Okay? So in your practical, when you do the simulation of bone work index, that's one of the aspects you'll be looking at, how much particles or how much load is calculated back into the mill. Okay, so what is the current grinding circuit, or what's the typical grinding circuit that you find currently? It depends on a number of factors, obviously. So you have the available technology. Okay? For example, I mentioned about ISA mills, Verti mills, or tower mills, and so on. So here in Australia, it's very common technology nowadays. If you have to do fine grinding, you can use what's available to you. Okay? So obviously, technology matters, what you can access matters, but also what is the nature of the ore itself. So how fine do you need to go, or how coarse do you need to keep it? Again, if I have to go to 10 micron, 20 micron, then I have to look into ultra fine grinding. If my target is about 500 micron, then maybe one stage of grinding will be. Maybe one stage of crushing, one stage of grinding will be. If I have soft rock, I know places where they do only one stage of grinding. They don't do any crushing, they don't do anything, they just do one stage of grinding with a ball mill, and that's the combination section. Okay, so there's no need for complicated crushing or complicated grinding if you have a soft rock. So it really depends on what you have and also what happens next. So after grinding, am I going to use a gravity separator? Am I going to use flotation? Am I going to use straight leaching? If it's straight leaching, you probably have to do fine grinding. Okay? If it's gravity separation, you have to do coarse grinding. If it's flotation, particles need to be intermediate, somewhere around between 100, 150, you can go as low as 50 microns. But it needs to be a medium size. So again, the downstream processing that you're going to employ also matters. Obviously, above all, your liberation size is what's critical. Have I liberated the particles at 250 microns? Have I liberated them at 100 microns? And so on. Maybe you will need to go to 7 microns, like I was showing you earlier. Again, that will dictate what's going to happen or what kind of circuit you're going to use in grinding. But generally, what I have here is what is observed these days in the industry. Okay? You could do 3 stages of crushing, rod mill, ball mill. Very less common these days, being replaced by this one shown in blue. Okay? You crush it with jaw crusher or gyratory. You use a SAG mill and then you use a cone crusher, as I was showing you earlier, to crush whatever comes out from the side mill, and then you have a volume as the final grinding operation. Okay. If you have very hard rock, okay, competent rock, very difficult to get, then it's probably better to use high pressure grinding followed by volume. Or maybe even one stage may not be enough. Maybe you can have 2 stages of high pressure grinding rolls followed by volume. So again, all these will be dictated by a number of factors, but the main one being the mineralogical characteristics of the ore. Okay, typical. So if you go to many gold plants around here, okay, so typically they will have either a jaw crusher or a gyratory as the crushing stage, followed by a SAG mill. And the SAG mill is operated with a screen. So oversize goes back for crushing, undersize goes directly to a cyclone. And the cyclone basically screens fine and coarse particles from one another. Fine particles can go to leaching and liquefaction and so on. Coarse particles are now sent to ball mills where you can do the grinding operation. And the ball mill discharge here is sent to the cyclone. The fine goes, coarse ones outside. So again, as you can see here, those the SAG mill and the ball mill are operated in closed circuit. Okay. So when I say closed circuit, SAG mill, screen, back again, SAG mill, screen, back again. So this is closed circuit. So I control the product size coming from the SAG mill. And again here is a ball mill it, send it to cyclone, oversize comes back, mill it, cyclone, oversize comes back. So again, this is a closed circuit. Again, this helps us with controlling the grind size that comes from the volume. Okay? So that's why we do those in different aspects. So this is just an HPGR based circuit in a gold mine. It's actually a copper gold mine in Western Australia where they employ high pressure grinding rods. Okay? So the high pressure grinding rods are actually followed after primary crushing, high pressure grinding rods, and then volumes, and that can be a good progression if you have competent road. Okay, so probably briefly go through what factors affect grinding rate. So mill speed, volume of grinding medium, mineral loading, torque density, and so on can be very critical when you do your grinding operation. So I think I probably mentioned this one a few times already, but for mill speed, it's all about the critical speed. And the critical speed is calculated based on the diameter of the mill and the diameter of the hole used inside the mill. And typically, grinding rate is very high, somewhere around 80% of the critical speed. Above that, grinding starts to drop as particles stick to the wall of the mill. Okay. For discharge, ball charge or volume, this is the amount of ball we load into the mill. Again, I mentioned earlier, about 40-45% is maybe the ideal. So in this case, about 45% of the mill volume is occupied by the ball or the rod. Okay. Why are we seeing this kind of grinding efficiency? Because initially, if you have too small media or too small balls, particle to ball contact is not as effective. You have too many particles, but too little media. So as you increase more and more of the media, you increase the particle to ball impact or the rod to particle interaction. Okay. But once you hit a certain level, say about 50% volume, if you just keep adding more and more ball or more and more rod, eventually what happens is instead of the particle hitting the ball hits the ball or the rod hits the ball, simply because you have too much loaded in the mill, and therefore your grinding efficiency starts to drop. Okay? Because the contact between the media is a lot more higher than the contact between the particle and how about rock filling? In this case, how much charge you put inside the meal. So this one, x-axis, is rock filling, and the y-axis is again breakage rate. So again, if you have too little material to crush inside the mill, the grinding is low. Okay? So effectively, you need to add more and more of material to grind to improve the grinding rate. Because at low loading of the particles, all that happens is ball hitting ball or rod hitting ball. Okay? I need to load more with the particles. So more and more particles loaded means contact with particle and ball increases, and therefore that helps with breakage or grinding. Again, where is optimum? The optimum is somewhere around between 15 and 20% of the meal occupied by the rod. Okay? So somewhere around 15-20% gives you a very good breakage rate. And these are just a comparison for different loads of balls. Okay? So these numbers here, 0.3, 0.35, 0.4, 0.4, 0.45, this show the loading of the ball. Okay? So basically this one, how much ball we have added in the mill in percentage. So in all cases, somewhere around 15 to 20% of the mill volume occupied by the particles gives you a very good breakage rate. Okay. What happens if I keep adding more and more particles? Eventually, what happens is I will overload the mill. Instead of particles hitting the media, I have particles hitting particles. Okay. And that should reduce your grinding rate. Ball size, I think to put it simply, smaller balls are more suited for finer grinding. Larger rocks or larger balls are more suited for coarser grinding. And this is all to do with momentum. Okay? Large rocks have large momentum, can impact on large particles. Small balls have smaller momentum and they can impact with small particle grinding. The other factor is, of course, surface area. Small ball has higher surface area, more contact with particles. Larger ball, smaller area than particle ball. But generally speaking, if I have to do fine grinding, I would use smaller media size. If I have to coarse grinding, I have to use larger media. Okay, so these are some of the factors that you can consider when you decide what size of ball or what size of media you're going to. And to give you an idea, nitrogenous mills, somewhere over 100 is typical. For ball mill, yes? Okay. ይሄኛውን ጨርሻለሁ። አይ ቲንክ አንድ ስላይድ ነው። ስለዚህ ሌላ አክቲቪቲ ነበረኝ፣ እሱን እንትን እንላለን፣ ሌላ ጊዜ እንሰራለን፣ ወይ ደግሞ አፕሎድ አድርግላችሁና ራሳችሁ ሞክራችሁ የሆነ ጥያቄ ካላችሁ ልጠይቁኝ ትችላላችሁ።
ስምንት ተኩል ስላላቸው እስከ 8 ተኩል እንጨርስና ቀጣይ ወይ ሌላ ፕሮግራም እንትን እንላለን ወይም ደግሞ አፕሎድ ይደረግ።
ይሄኛውን ጨርሻለሁ። ይሄኛውን ፓርት አይ ቲንክ that was the last slide anyway። ይሄኛው ፓርት ያኛውን ዝም ብዬ አፕሎድ ላድርግ ነው። ኤክሰርሳይዝ ነው፣ አንዳንድ ካልኩሌሽን ያለው ኤክሰርሳይዝ ነው። አይ ዶንት ቲንክ ኮምፕሊኬትድ አይመስለኝም። ስለዚህ አይ ቲንክ ጥሩ ነገር ሊላክልህና እንደባለፈው አፕሎድ አድርግ ለልጆቹ። ሁሉም ሰው ይየውና ጥያቄ ካላችሁ ትጠይቁኛላችሁ። ኔክስት ነው አይ ቲንክ ሌላው ነገር ኔክስት ዌንስዴ እና ተርስዴ አልኖርም። አሁንም ወደ ማይኒንግ ሳይት ሄዳለሁ። ሪሞት ኤሪያ ስለሆነ ብዙም ኢንተርኔት አክሰስ የሌለው፣ ስለዚህ ምናልባት ተርስዴ አፍተርኑን የምንመለሰው። ተርስዴ ካልቻልኩ ወይ በዚህ ሰዓት እናደርጋለን። ፍሪ አይደለም ይሄ ክላስ ፍራይዴ
ለቀጣይ ይሆናል። ቀጣይ ፍሪ ነው። ቀጣይ 2 ሰዓት
ከሆነ አይ ቲንክ ኢሜል ልክልህና ወይ አርብ እናደርገዋለን ኔክስት ዊክ ሞስት ላይክሊ ሐሙስ ከደረስኩኝ ሐሙስ እናደርጋለን እነግርሃለሁ። ኦኬ ኦኬ። ስለዚህ ይሄኛውን ፓርት ጨርሻለሁ። ጥያቄ ካላችሁ ጠይቁ፣ አለበለዚያ ያው ይላይዛ ላግ መከተል ነው። ሪኮርዲንግ ከጨረሰ በኋላ አፕሎድ አደርገዋለሁ። እሱ ማየት ትችላላችሁ። ምናልባት ቴክኒካል
ጥያቄያችንን ጽፈን ለቀጣይ ብናደርገው፣ ምክንያቱም አሁን ውጪ ፒኤችዲ ዲፌንድ የሚደረጉ ተማሪዎች እየጠበቁ ስለሆነ፣ ስለዚህ ቀጣይ ሐሙስ ወይም አርብ
ሐሙስ ያው ላልደርስ እችላለሁ። አርብ በሚለው ነው ያለው።
ስለዚህ አርብ ቀጣይ አርብ ዲፌንስ ይኖራል ብለን ስለማንጠብቅ 2 ሰዓትም 3 ሰዓትም ማድረግ እንችላለን። እናመሰግናለን።